Okay, so let me just say a couple of words. All right, everybody. So this is part 2 of our workshop for AI for materials. So this one's focus is on neural network potentials. Last week we had it on our last session was on graph neural networks in general. So this is a bit more specific and on topic to what a lot of your domains are. And we have here with us Corin, who has a startup called Rowan Sci. And they integrate some of these neural network potentials. They've worked a lot with them, and et cetera. So he definitely has some expertise, particularly in the medicinal domain from what I saw. Without further ado, though, Rowan, I'll leave the floor to you.
Thanks, Amir, for the intro, and thanks for putting this all together. Is it possible for me to like visually see who's in the room, just for like context, just so I can wave? It's kind of abstract giving a talk to the ceiling.
I'll do it via my camera.
Oh, it doesn't need to be prolonged. I just want to see your beautiful smiling faces.
The few that did manage to show up are here.
Hi, folks. Nice to meet you. Yeah, so let me, so I was given some instructions here. I'm going to talk a little bit about like neural network potentials, sort of in general. So a little bit about like who I am, a little bit about like what are neural network potentials, why do we care, trying to ground this scientifically. And then we'll do some code workshop and then some like more higher level workshops visually. And then sort of talk about where I think this field is going and stuff to pay attention to. So that's sort of the high level overview of what we're going to try to cover today in the time that we have. And please, at any point, please just yell at Amir or Mehdi or whomever, or just yell at me to interrupt so this can be dynamic. It's much more fun that way, more of a workshop, less of like a State of the Union address. I don't know, do you guys have that in Canada? We have that in the US. It's pretty boring.
We've been having a lot of any sorts of meetings publicly with the people from our politicians. So
that's true. Okay, so yeah, let's not do that. Okay, I'm gonna share my screen if I'm able to. All right, is this coming through okay?
Yep.
All right, so yeah, this is about neural network potentials, which are sort of a subclass of GNNs. So you guys have already talked about sort of like geometric deep learning, graph neural networks. I mean, this is intended to sort of be like a specific deep dive into like one area of like ML for science, material science, chemistry. I'm a chemist, so I think of this in terms of chemistry, but it's equally as important for material science. And I'll try to focus on that much more today. So just briefly about me. So as I mentioned, I'm actually a chemist. So I worked on like ion pair sensing before, homogeneous catalysis, reaction mechanism, analytic chemistry. And my journey to sort of like computation and simulation was very roundabout. So I used to work in a lab and derived a lot of joy from that. But the more I studied reaction mechanism, the more sort of it became clear to me that like simulation and being able to actually model what was going on was going to be like one of the defining and I think transformative sort of technologies of how we approach, atomistic sciences. So chemistry, biology, material science, chemical engineering. And sort of the way I got there and got so interested in ML was just by really encountering like very harshly sort of the limits of conventional simulation. So I promise this is not an organic chemistry talk. I won't do very much organic chemistry, but I did used to be an organic chemist. And one of the things we were trying to study was this sort of mechanism. So how this reaction happens. And, those of you who have some experience in reaction mechanism can probably guess that like, you can either do this in a concerted one-step sort of 2+2 process or a stepwise process. We did a bunch of like various NMR experiments and we convinced ourselves that it was happening through this stepwise mechanism, but all of our calculations essentially showed that it should be operating through a concerted mechanism. And so what we had to do in the computer to finally get the correct mechanism out was we had to explicitly model hundreds of solvent molecules surrounding this. So we had to actually use the like sort of the nuclear option of explicit solvation to model this mechanism correctly. More abstractly, and okay, I think this is the second of 2 organic chemistry slides. You can actually model the free energy surface and show that not modeling the solvent, so doing what people usually do, gets it wrong. But when you actually throw in hundreds of solvent atoms, you actually predict an intermediate in the top left here, like a minimum on the energy surface. The problem was that even for this tiny, tiny system, so we weren't able to model more than like 20 atoms using this way. So these explicit solvent simulations on the right here. A single MD time step to model this reaction took about 5 minutes. And that gives you 1 femtosecond of time. And we had to run to converge this surface just barely. It's not even very well converged, but it took almost 3 nanoseconds of simulation time. And so if you sort of crunch that math, this works out to about 25 CPU years of simulation time, or that's about 200K worth of money just to model this one simple reaction. And so sort of, I think this is emblematic of a lot of challenges that like simulation in the chemical sciences faces, which is just that like, it's really hard and it's hard to get answers that are worth having. And so practically we often just don't do simulation at all. So I think this is even more apparent if we sort of compare industries like a long time ago versus today. So this is Fairchild Semiconductor in the 1960s. This is how semiconductors work now. It's super computerized, a ton of computer intuition involved in laying out chips, designing all this stuff, positioning elements, monitoring heat flow. This is chemistry in the 1910s. And this is what my lab bench looks like when I was doing like antibiotic discovery. You know, the flasks are different. So the instruments have gotten a lot better. There's more things you can buy now, but fundamentally, it's still an experiment first field, as is true for a lot of polymer science, a lot of materials discovery. It's sort of like do experiments first and maybe do computations second to figure out what we did, if we can do that at all. In a broad sense, I think this is just because it's really hard, what I mentioned. So modeling heat flow and fluid flow, these are hard problems, but chemistry and material science are harder. So reactions, biomolecules, surfaces and catalysis, solutions, right? Electrolytes, ionic liquids, dissolution, even just modeling like sodium chloride in water turns out to be really, really, really hard to get right. And so these, I mean, this is like pretty much everything we care about at a high level, right? Like either solids, liquids, polymers, reactions. I mean, this is the whole field on some level. And so I think, you know, faced with this, a lot of people have sort of given up on simulation a little bit, like it's impossible, we'll never be able to do it. But it turns out that a lot of deep learning approaches are still struggling. So deep learning methods that try to circumvent physics often behave in very unphysical ways. So this has been the most studied, I think, in protein ligand docking, where you're trying to model how biomolecules interact, where you can show that all of these AlphaFold 3 type methods suffer from really bad data leakage. So as you move away from similarity to the training set, the success rate approaches 0. So we're not learning physics correctly, we're almost just memorizing. Even when we do get the correct pose, often it's not actually physically valid. So the bonds are in weird places, the geometries are insane. And then even in these cases, it turns out even when we get it right, we can actually remove the binding site and see that the prediction is still the same. So even the correct pose for the correct ligand is still not quite learning the physics of protein ligand interactions right. Like if you fill up the binding site with bulky residues or you delete everything and take away all of the key interactions, it still predicts the same pose. And I think what this shows is sort of like it's an appealing idea that we can just get rid of actually simulating things and actually caring about the physics, but it's not yet really possible. Like it's not it turns out like actually being able to simulate things is still really valuable. And so what this talk is going to be is sort of how we can address this like sort of this quandary, like this big issue that faces our field of like simulation doesn't work. We'll talk about why it doesn't work, how we can try to solve this with neural network potentials, and sort of then what this actually looks like in practice. So sort of 2 state-of-the-art simulation methods, just to give context for like what happens. You know, what does it look like to simulate something right now? Why doesn't it work? One way is we actually do all this quantum mechanics. You know, we do density functional theory or something similar. I'm sure you guys have heard of that if you've done any computational work. So you generate orbitals, electron densities, all this fun stuff. And this looks like, you know, there's a ton of softwares here. So if you've ever used one of these softwares, that's doing some sort of quantum chemistry under the hood. Yeah, and this field has come a long way, right? So it used to be the like 8 atoms. This would get you like a state-of-the-art paper at a very low level of theory. And now, you know, like 4 decades later, we can do like hundreds of atoms with pretty good accuracy, and we can actually match experimental values. The problem is that this is still just like so slow. So in the US, the UK, and Japan, this accounts for like a sizable fraction of all national supercomputer time in like national labs and supercomputing centers. So we did a study here on our blog. It's like 20 to 40% on average, sometimes more, mostly just VASP. It just turns out that scaling this stuff to the big systems, to the stuff we actually care about, is really, really expensive. And you can scale this. So if you sort of pour more GPUs on the fire, you can scale it. So you can use 500 tensor processing units from Google, and you can get like, 10,000 water molecules. You can use 27,000 GPUs, and you can get to like 600,000 electrons, 150,000 atoms. And then, people have actually been able to break the 1 exaflop per second barriers. So exa is like beyond tera, I don't even remember what it is. And you need like 10,000 different compute nodes to do that. And so this is fine, but this is clearly not a fantastic solution because it takes a ton of power, it takes a ton of money, it takes a ton of resources. And it's just like, average researchers will never be able to do this. Like we don't have exaflops of compute lying around to give to graduate students or startups for that matter. So this is clearly sort of like not a very good solution for the simulation problem. The other solution is molecular mechanics. So this is sort of where things go on the other end. So if you want to study like big boxes of solvent or big proteins or big polymers, we say, well, we know what bonds are like, we know what angles are like, we know what dihedrals are like. Why not just sort of like put those in? We'll have a simple function. We don't have to do all this coupled differential Schrodinger equation math. And we can just sort of put in the physics that we know and understand well, and this will probably behave in a sane manner. So this works. This makes things really, really fast, but it's a little too simple. What you get out of this is like very massive errors. And at this point, there's like pretty big molecular mechanics related issues with the shape of molecules, the structure of polymers, sort of dynamics of protein folding, free energies in solution. So, it sort of qualitatively gives things that are semi-sane, but when you actually scratch the surface and you start trying to make predictions off of these simulations, you find that they're really, in many respects, quite disappointing. Not in every case. There's a lot of people who do really good work in the space, but it sort of doesn't quite feel like a solution that gets us to where we want to go in terms of like predictively accurate simulations. And I think, honestly, material science does this to a much lesser extent than drug design, simply because the field is more complicated. There's more things to study, and the shortcomings of this solution are much more apparent. And so this sort of, when I started doing computational science, this was sort of the state of the art. So there were like, this is a plot of how slow things are, so a logged scale of time. This is for evaluating shapes of some molecules and ranking them. This is like the accuracy relative to experiment, so the R squared, the correlation with the truth. And you can sort of smash a piggy bank and spend like weeks on each molecule and get the right answer. You can get answers really, really fast, like virtually instantly, but that are like very bad. So an R squared of 0.4 on an easy task like this is pretty disappointing. And then you can sort of go anywhere along this frontier you want. So you can be fast and inaccurate, you can be extremely slow and accurate, or you can be pretty slow and pretty inaccurate. But sort of none of this is really where we want to be, which is in this top left corner, right? So we'd like to be fast and accurate because that's actually how we can do useful science. And sort of like it seemed like there's this unbreakable relationship between the more accurate you got, sort of like every linear increase in accuracy demanded like an exponential or a order of magnitude increase in cost. So this sucks. Basically, this sucks. Okay, so this is where we sort of bring in neural network potential. So against this backdrop, this is why NNPs are so exciting. But before we talk about NNPs, I think it's worth acknowledging that sort of the core idea behind an NNP has been used since the 1960s, actually. And this is to say, like, well, if I just want to study one system, like for a really, really long time, I don't need to solve quantum mechanics at every single step. I can just solve a bunch of quantum mechanics once and then fit a polynomial to the potential energy surface. And so we might say, for a very simple system, H3, where we have 3 hydrogen atoms, like an H atom and an H2 molecule, and those can react and combine in different combinations, we can actually plot with a fairly simple function what the potential energy surface looks like. So say this is one distance, this is another distance, there's an angle term that's not captured here, but we can basically just make a plot of the energy, and then we can run molecular dynamics, we can predict vibrational frequencies, we can find minima, like we can do anything we want once we've put in all the work to build the potential energy surface sort of analytically. And indeed, you can find papers that they put a functional form, they say, and then we fit all these constants, and this is what we got. These are the 7 constants, and we pretty much can get the exact thing perfectly right within the limits of our precision. And then you can do a ton of really interesting science on the H3 system with this, because you've essentially got a solution that is both fast and accurate. The problem is, one, it takes a lot of work to get that, potential energy surface fit. And two, this approach really, 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 really does not scale. So, this is again a system I showed earlier that I worked on. This, the single sort of metal atom, single ligand, it's not that complicated in the grand scheme of things, but this has 342 internal degrees of freedom, right? So to think about like writing a polynomial or some other function that actually, has 342 individual variables, each of which depends, influences the energy in some sort of way, is just like a very, very difficult task. Like it seems impossible. Furthermore, there's sort of this issue of permutational invariance, right? So like, I shouldn't care which carbon is in which spot. Like you want the function to sort of have this permutational invariance property. You maybe want it to have rotational invariance. And you start kind of encoding all of these things that like, how do you write a function that satisfies all these constraints? How do you make it scalable? How do you make it so you can even like fit all these parameters with so much data? And by this point, this is probably starting to sound pretty familiar. Like, oh, wait, I think we know functions that can do things like this. And this is exactly where we sort of bring in the idea of graph neural networks. So graph neural networks applied to potential energy surface prediction is just a neural network potential. So that's all it is. A neural network potential is just a GNN that takes atomic positions and gives you properties out, most commonly the energy and forces. And believe it or not, this is actually done as long ago as 2007. So this is like the first true NNP. And this is Jörg Beller, Michel Parnello, the fantastic physical chemist. And he basically outlines these exact reasons. He says, DFT is too slow. We can create a high dimensional potential energy surface. So not like a low dimensional potential energy surface like H3, but a high dimensional one by using a neural network to represent the DFT potential energy surface. And this has like a number of really good advantages. So it's flexible, it's permutational invariant, and we can construct it in such a way that it's local. So we can use like a cutoff graph method like this so that each atom's energy only sort of depends on its neighbors and not on the whole thing, which makes this much more easy to train. Okay, I've been yapping for a little while. Do you guys have any questions or thoughts? I can't actually see you guys right now, so let me back off and and take a quick break.
Does anybody have any questions? No? Okay, so far in person, nobody has their hands up.
Okay, Amir, can I task you with just yelling at me if people have questions?
Yeah, sure, will do.
All right, very well. Okay, so I'm not going to go through, history is good up to a certain point, but I think it's worth just sort of fast forwarding from 2007 to today. So 2007, I'd say the first NNP was for amorphous silicon. And so this is like a few thousand learnable parameters and then a few thousand DFT calculations of training data. In 2012, Beller strikes again with a neural network potential for liquid water. So this is now obviously a bit more complicated. You have multiple types of atoms. You have sort of a much more directionally oriented system. But then I think in 2017 is the real next breakthrough for the field. And this is the release of ANI-1. So this is a general neural network model for neutral closed shell organic species with C, H, N, and O as supported elements. And essentially what this means is now we don't have to train a new neural network potential for every molecule under study, which takes a while and demands sort of specialized expertise. We can use this sort of foundation type model that can generalize to unseen molecules that are comprised of the same building blocks. So we're not generalizing to unseen elements. So Annie doesn't know what to do with fluorine, for instance, or iron. But nevertheless, if you have a molecule that sort of fits within the scope of like non-charged closed shell organic molecules, you can probably get pretty good performance with Annie. And so this is about 500,000 learnable parameters, and it's trained on almost 20 million DFT calculations. So this is actually, it's pretty cool just to look at the results from their paper. So these are torsional scans, so rotating around the numbered atoms and seeing how the energy changes. And you can see that the training data, the ground truth, at least for Annie, is in black. The Annie performance is in red. And then two other sort of low-cost computational methods are shown in blue and orange. And you can see that Annie is getting things like substantially more correct than the other low-cost methods. And so this is like a pretty nice success. And it's worth saying that also all of the DFT calculations here were on 8 or fewer atoms. And so these molecules shown here aren't just not in the training set, but like no molecules their size are in the training set. So you're generalizing, you can't generalize to unseen elements, but you can generalize sort of from small to large, which I think is pretty interesting. And thinking through what dimensions are easy or hard to generalize along is like, I think an open question in NNPs and one that deserves careful study and that we can talk about more maybe at the end. So sort of where are we at now? I'd say there's like two.
So Corinne, sorry, I think we have a question.
Hit me.
It's gonna like vibrate a little.
Hold on, let me kill the echo.
Can I just yell in that microphone?
Wow.
Hi, Corin. We're just trying to fix the reverberation issue here.
That's great. It sounds kind of spooky.
Can you go back to that picture of all of the different models modeling the rotation? You said
Yeah.
Annie did the best, but
Mhm.
what are you comparing it to? Like, do you have an actual chemical reaction that you can compare and say Annie is doing the best?
Right. So in this case, they're focused on just learning from this sort of quantum chemical surrogate function, DFT. So we can benchmark different DFT methods against like very high level computations or against gas phase values in this case. And we can show that like, if you spend enough money in the computer, you can pretty much approach the ground truth for this. So like, this is a task for which in the gas phase, DFT does very, very well. The method that Annie authors used is like fine. So it's omega B97X 631G, if that means anything to you. So it's like not, it's not amazing, frankly, but it's decent. And it's definitely like, I think within the realm that you expect it to be much more accurate than the blue or orange here. So I mean, I think more broadly, there's always sort of two questions within NNP. It's like, how accurate is the model at fitting the data? And how accurate is the training data relative to like the objective truth? And you obviously the observed error when you have an NNP versus truth is like the sum of those two errors. And what this shows is just that like given a set of data, Annie can learn it like very, very well. And it doesn't really address the like how good was the data in the first place. Does that make sense? Or does that answer your question?
Yeah, partly.
What would
Sorry for the spookiness.
No, it's fine. What would answer the other part of your question? Or like do you want to
Well, you're just showing a graph here of different models, and you mentioned Annie is doing far better than the DFT or the other two blue and brown models.
Sorry, I understand what you're saying. No, so Annie is trying to fit the DFT. So it's
Black is like
agreement with black.
the black is the one that we believe
Trained.
is truth.
Yes. So for the purposes of this experiment, this is truth. In real life, it's pretty close, but it's not exactly perfect. But you can see here they quantify the RMSE relative to the oracle function, essentially, which is in black. And so in this case, Annie is 0.4 away from the oracle. The blue DFTB is 0.7, and then PM6, the stars, is 1.5. And then over here, for lisdexamphetamine, it's even more apparent. So Annie is 0.9, whereas the other two are like over 4 kcals RMSE.
Okay, makes sense. Thank you.
Yeah. So yeah, I mean, I think the question is like, if we use really, really high quality data, can we still train to that? And the answer, I can send you the papers. I don't have them in these slides, but the answer is basically yes. Actually, the Annie authors did this later. The problem is like acquiring the really high quality data ends up being so expensive, you can't acquire very much of it. So you don't get the same generality. So I think like one of the big open questions in this space is like, how do you balance getting enough data versus getting good enough data? And that's we'll talk about, we can, I have a slide on fine tuning later, but basically there's a few ways to approach that, but it's like something you have to think about pretty carefully in general, I'd say. Yeah, good question. Okay, so like where are we at now? This is my summary, so take this with a grain of salt, but in my mind, there's like two sort of big buckets of neural network potentials right now that exist. And this field has blown up in the past like 2 years, by the way. This is probably one of the hottest, if not the hottest area in like computational chemistry and material science. I'm clearly biased, but I think it's, probably has the most activity because I have to read all the friggin' papers. So there's material science focused NNPs. So this is things like MACE MB0. A bunch of the big tech companies have gotten involved. So Mattersim, Gnome, OMAT24, and then some startups like Orbital Materials. And these are usually trained on like the entire periodic table, a lot of inorganic materials, a lot of like battery looking stuff, a lot of like perovskites, etc. And then on the other category is sort of these bioorganic NNPs. So that's much more like Annie, where you're focusing on carbon-based molecules, water, stuff like that. So much more things that would be in biology. And you usually can't support like random leads or irons thrown in there. And so these are sort of like different training data construction. Like if you have a given amount of training data, do you put all your points into just like different looking organic molecules, or do you try to spread them evenly throughout the periodic table? And they end up being good at different things. The scale today is like big for like chemistry, but pretty small for ML. So usually under like 200 million learnable parameters or fewer, and about that many DFT structures. This might seem weird, like it's weird that you have like one-to-one parameters for training data, but it actually isn't that weird because each DFT structure has a ton of like per atom information. So there's actually like sort of, if you imagine like what's the token equivalent, there's like many more tokens than 200 million, but that's like how many structures there are in general. And I think it's worth to say there's like a ton of progress in this field, and over the next 12 months, I'm sure that these lists will probably almost completely turn over. So yeah, pretty fun. Yeah, and it's, you know, one of the big things here is just like it's a zoo, frankly, to keep up with all this. People have made jokes about this, and like benchmarking and figuring out what's good for given applications is like an incredibly valuable and useful activity, as with sort of all other fields of ML right now. So I want to just share sort of like one story on the benchmarking, just to sort of show what this can look like, and like, just because it's the work that we did and I got invited to speak, so I'll talk about my benchmarking work. There's a lot of good benchmarking work out there. One of the things I think there's always a question for these is like, how generalizable are these models? And so like if we, you know, if you give it a weird looking molecule, will it just freak out? Will it start hallucinating? You know, when do these things break down and stop being reliable? And so one of the ways that we tested that in collaboration with the GARE lab at Michigan State University was we just took these like 3 pretty simple molecules that have a bunch of different sort of structural features in them, and then we just like tormented them. So we ran metadynamics and extracted the weirdest possible poses we could find. And so what this gives you is like huge differences in bond distance, so like up to over 10% of the bond length, which you never see ordinarily. Big differences in bond angles, big differences in dihedrals, and like really massive relative energies. So like these are very, very unhappy and strained structures that are pretty likely to be underrepresented or not represented at all in the training data. And so we compared ours set Wiggle 150 is what we called it in green to like the conventional sort of conformer sets in black. And you can show that their dihedrals are all like very close to 0 relative to the ground state. So that, you know, we're really creating much weirder geometries. And what we find, there's a ton of different methods on this slide, but it's essentially another version of like time. So fast on the left, slow on the right. And then like here, we're looking at RMSE. So good is on the bottom and bad is on the top. And what we see is like, if we ignore the green, which is the neural network potentials, you know, like force fields are fast and bad. Semi-empirical methods are like medium good and medium slow. And then DFT is like good, but very slow. And what we can actually see is now like, if we look at all of these green dots, some of them are not great, but some of them are really, really good. So this is like where we want to be, right down here, where we're fast and accurate. And specifically, so these 2 are the organic focused ones we studied, and these 3 are like the materials ones we studied. And so for this task, the organic ones do well and the materials ones do much worse. And that kind of makes sense because it's like an organic task. So if we looked at a materials task, the materials ones would do well and the organic ones would do poorly. So you do sacrifice some generality, at least with today's models, but in exchange, we're like 8 orders of magnitude faster than like what a comparable method would be. So, you know, so this would take like about 10 to the 4th seconds, and this takes like 10 to the negative 4th seconds. So that's a pretty good speed up, I'd say. And that's part of why this field is like so exciting, because yeah, you have to check that you're doing everything right, but you can legitimately speed something up by 8 orders of magnitude for the same accuracy. And like, you really don't see that very much in science. So it's worth taking seriously when you do. Okay, so I think maybe now is a good time to like move over to actually like what does this look like in practice? How do we do this? Like, how do we do this? So I thought like we could look at this solid state like crystal benchmark set, because it's some of the cleanest like solid state benchmark data out there. And then look at MACE MP0, which is one of the like most commonly used materials models on trying to reproduce that data. Does that sound good to everybody? Any questions before we like switch gears a little bit? Very well.
There's no questions on our end.
That's great. I'll take your silence as acceptance. Okay, so here, oh man. All right, Google Colab, I was trying to use for this. I usually don't use Google Colab.
Can you
So
share the link?
yeah, I can.
Chat?
Can you guys see that?
Yeah.
All right. And let me see. So let me stop sharing my screen and figure out how to share the data with you guys too, because I realized I linked the data in from my Google Drive, but that might not work as well for you guys because you actually don't have access to my Google Drive. Share. All right, so here's a link to the data. So it's just what this benchmark set is X23. So it's a set of like molecular structures and solid state structures. And what the task is try to predict the lattice energy, which is like, I don't know, it's like it's a pretty good test of like how well you're capturing the like stabilization from crystallinity. And if you, it also comparing lattice energies lets you find the polymorph. So it's like a pretty important like crystal structure prediction thing, both in pharma and like various inorganic materials type stuff. So let me share my screen again. All right. So, well, I can't see a show of hands, but we'll be using ASE for this, which is like probably the most common like material science simulation package, so the atomic simulation environment. And then here we're going to look at two different NNPs. So there's MACE Torch, which is the pip installable package for the MACE MP0 model. And then there's the Orb models package, which is from Orbital Materials. So these are like just two of the sort of common foundation models for materials simulation. So if we install these, it all kind of works. You need Pi nanoflon for Orb models, but they didn't include it in the requirements for whatever reason. And then we can import all of our stuff from ASE and from these models. Okay, and so sort of what this is going to look like. Again, apologies if you guys haven't used ASE before. But what we're going to want to do here is essentially we take in a molecule, like an isolated molecule, we optimize that and get the energy. We take in a solid, like a crystal structure, and optimize that, including sort of the box volume, and get the energy from that. And then we sort of take the energy of the solid minus the energy of the molecule, modulo however many molecules per cell to make sure we do our math right on the energies. And that'll give us back, we'll return both the lattice energy and the cell volume. So sort of how tightly things want to be together and how big the cell ends up being. And there's, what's nice about this benchmark is there's actually really good experimental values for both of these, for all of these compounds. And so this ends up being like pretty easy to check and see how we're doing. And so what we're going to do here to sort of load in like a neural network potential, we'll take in this ASE calculator object, oops, which I actually left out of the doc string. There we go, fix that. And so this, you know, ASE calculators can be anything. So it could be DFT, like it could be VASP, it could be Quantum Espresso. But in this case, almost all neural network potentials ship with like an ASE calculator interface. And so since they're pre-trained, you actually don't need to do anything. You basically just load in the model. And then when you call inference on the model, it returns you an energy or a force. And it's basically just the same as working with DFT, except it's way faster.
Corin, can you?
Yeah, hit me.
Can you make the Google Colab open or?
Oh yeah, what have I done wrong here?
So the drive for the data is also locked, so we don't want to spam you a bunch of it. What?
All right, that's great. Thank you. Thank you guys for saying that. Okay, it should be shared with anyone via link now. That work?
Let me refresh.
Yeah.
Yeah, okay. Yeah, open with Google Colab.
That should be right.
Okay, so the Colab works.
Okay.
And I don't know the data later on. We need access to that data, or can we get it through MatPy?
So this data I don't think is available on PyMedGen. I scraped it from an SI and like formatted it. So this is a great question. These are really good questions you're asking that I should have thought about before right now. Because I didn't think about how people would want to follow along. So can you guys open the Google Drive link I shared in the chat? Is that, it says it's shared with the world. Is that like true?
Let me check.
I can,
Yeah,
when
I see the two folders. Yeah.
okay, when I open an incognito window, it does work.
Yeah. Yeah.
Okay, so now let's see. It might be easiest if you guys download that. I think there's a way to upload things. You can just upload the folder directly to como se dice, to Google Colab. So let me just try that right now. Let me download it and try uploading it. If anyone has a better idea here for how to do this, please let me know, as I am clearly. No, we don't want that. That won't work for you guys. All right, well, we'll just download all these files.
Yeah. I think just manually download the folder and move it over.
Yeah, I think you're right. All right, so if I download the X23 folder, I'm doing this now. It's zipping. Thanks for your patience here, guys.
So just, I don't know if it's this first section here, but when it references the code to read the files, we have to reference it to the local folder, right?
Yeah, so what I'm doing here, so let me delete that because this is not going to be as helpful. So I was just mounting it from my Google Drive, which is kind of slick, but so let me just delete this. This is mounted from my Google Drive, delete folder. Okay. Okay, whatever. We'll rename it because I can't delete a non-empty folder. X23 bad. We won't use that anymore. So let's go here and we'll create maybe a new folder. Okay, so we'll put stuff in sample data. So it's a new folder, and we'll want a mols folder to store the molecules, and then we'll want a solids folder to store the solids. So now if I go into mols, I can now go to upload here. Can you guys see the modal pop up here?
The mole pop up.
The modal, the little window that pops up. All right. Okay. So here, let me switch from sharing the tab to sharing my whole screen. This is what doing computational science is like in the real world. Okay. So if I go here, so what I did was I went to upload here. So I have my downloads. I downloaded the X23 folder and then I copied all of the molecules in like this. And then I just loaded them all in right here. So they're all in ext XYZ format. So if we look at these, it's very commonsensical. Like it's just I don't know, one of the ways you can specify a molecule, go figure. So now if I try to move all of these, I can move them into molecules. All right, now the real question, can I select and move multiple in the Google Colab window? I maybe cannot. All right, we'll do them all one at a time. Hilarious. All right, we'll just do 3 for now. We'll get started with 3. All right, no, there's 5 in there. Okay, great. What's the best way to do this? I guess just drag them all. Yeah, so what I can't figure out is like how to, here's what I should do. All right, so we'll open this folder and then we'll upload them all directly into here so I don't need to drag them all. Boom. Sorry, I did do this all before the meeting to copy them in, but the problem is it deletes your runtime if you time out for too long. So all my hard preparation work was undone. All right, now we wait.
And if it doesn't work now, you just go with the files you have, and we'll handle the Google Colab after.
If you do this properly on your own computer, you don't run into these issues because all the data is just right there. All right, there we go. That worked. So we'll go back now. We'll go into solids. We'll say open this. we'll upload all these. So we have to go to solids, copy all of them, and upload those. All right. Wow, they said it couldn't be done. Okay, and this is folders and sample data, and I'm just going to rename it X23, just so I don't have to change any of my scripts. So now what we should have here, if you ignore all this other junk, is a folder called X23. It has a folder called mols, and then that has 23 molecules. Solids has 23 solids. Boom. Okay, so that's how that works, and we'll be able to delete this mounting from Google Cell. Okay, yeah, so this is the function. I mean, it's really not very complicated. You just optimize both of them. The one thing, so I'm not a huge periodic calculations guy. I do mostly drug discovery, but you have to use this like weird Freshet cell filter, and you can choose two different optimizers, quasi-Newton or Fire. For whatever reason, some work better than others with different neural network potentials, because the gradients end up being a little noisy relative to DFT, and so you have to choose somewhat noise-tolerant methods. So it's a little bit of trial and error. I think later generations of model are going to fix that, but for now, there's like you get a little spaz. So what this is, here we just sort of enumerate how many molecules there are per unit cell. So if we actually look here at like what the molecules are, the unit cell has varying numbers of things in them. And so we just have to like account for that when we call the function. And so then we'll just, what we do here is we say calc equals mace MP. So that loads in the mace MP model. So it's mace torch on GitHub, just to show you guys. There's like whole directions around this. You can set different options here if you want to. But just the default Mace MP sort of has like sane options. And this loads in the Mace MP0 model. We call our function and then we just click run. And it starts to work. So this is tracking sort of the energy, the maximum force to check for convergence, and sort of this step. So this is quasi-Newton, so it's doing a little BFGS line search. And what I think is just sort of like noteworthy about this is just like, one, it just works. So this is running on like literally a potato in the cloud. And we're still getting like multiple steps per second. And this, like, if you've ever done like periodic DFT or non-periodic DFT, like that, each step here could easily take like 10 minutes or an hour. So this is just remarkable sort of how fast this is. And I mean, I really think that's like sort of that's the beauty of neural network potentials. So if you're going to run a benchmark set like this with DFT and you wanted to actually do it like properly, you need like a high performance compute cluster. You would need like a bunch of resources. If you did it on AWS, it'd cost you a bunch of money. And here, literally, again, we have this potato in the cloud, and yet it still works. Like we've already done the first 3 values in our benchmark set. You could do this on your laptop. You could probably do this on your phone or like your smart, fridge or whatever. It requires very few resources. And what that lets you do is actually do like big MD studies on like long systems, which is awesome. All right, it's going to take a sec to get through all 23 of these. Any questions while this is running?
No questions on our end.
No questions. All right. No one wants to take pity on me. All right, well, we can look at the results as they come out then. So here's the first few. So this is like energy, lattice volume, and then time. So it's taking like 23 or so seconds to run each one. I have the reference values here. I scraped them from the literature. This paper is easy to find. But let me actually delete the ones that I had checked earlier.
So I have a question. So
Yeah, hit me.
we're feeding it 23 structures,
Mhm.
and it's going to just output 3 parameters here: volume, E, and time. Right?
Yeah, that's right.
Okay. So it's not being trained; it's already being trained.
Yeah, so that's sort of like the beauty. At least we're studying. So what we're going to find out through this is like how well does this work out of the box versus would we need to fine tune this? And I think it's worth sort of like for any application, right? It is like, I mean, this is always true with computations. You always need to benchmark them. It's even true for DFT. It's also true for this. You need to like compare carefully to what you want to do and like see, is this tool going to waste my time or is it going to give me something I can work with? Will this give me insight? Will this help me get somewhere? But for this, what's nice is like there's a sort of a like a menu of pre-trained ones out there. They're all a little different. So they have different architectures. We haven't talked about architecture at all, you'll notice. And that's because the architectures are like wildly different. And I'm very much a pragmatist, so I'm not like much of an ML theory guy. I understand some of it, but I just care about what works. So there's like, some are like equivariant tensor operations, others are like global attention, others are like message passing, like blah, 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 different featurization, different cutoff distance, all sorts of strategies out there are sort of being tried in parallel. And what's nice about about being an applications person is you just try them all at what you want to do, and then you pick the one that works best. And then if none of them work well, then you try to build a better one.
Okay, yeah, that was my next question. Seems more of an art than a science.
Well, yeah, yes and no. A little bit. I mean, picking good computational methods, I suppose, there's a little art to it, but it's quite literally science too, because you run the experiment to see how good it is, and then you follow the data and pick the best one. So I don't know, same as screening electrodes or something. We host some benchmarks here at Rowan just to try to keep track of what's good. So like some speed benchmarks, some like quality benchmarks for different models. So these are like some thermochemistry benchmarks here where we compare like different properties like errors against models. So this might be helpful. We're always trying to think of new benchmarks to add, just whatever's useful. Another one, there's MatBench Discovery, which is like sort of a different type of, they benchmark different things, but they do a bunch of benchmarking here as well too. So there is like data you can use to make these decisions instead of just vibes. Okay, let's see where we're at data-wise. Okay, some progress. So if we go here, we can start maybe drawing some preliminary conclusions even before we have all of it finished. So split the columns, boom. Okay, so if we look, we have two values essentially that we have from the reference. And so we have sort of what we expect the reference energy to be, and then what we expect the reference volume to be. So how big does the unit cell end up being, which like obviously tells you what the density will be and like some measure of the non-covalent interaction strength. And then there's like how strongly are these things predicted to bind. And what we see here is actually is kind of interesting. So we're seeing like the volume is predicted to be pretty much too big across the board. So that we're about 61% too big in the unit cell volume, which is actually like a pretty substantial difference. And then the binding energy is like strikingly overestimated, it seems like, if we look at this. So, what is this? Carbon dioxide is predicted to have a lattice energy of 7. Here we've got 11. And it's predicted to have like a volume of 41 cubic angstroms. And here we're at like 55 cubic angstroms. So I think it's safe to say it's like sort of, it's not horrible, but like it's not amazing. This is not like a fantastic performing method. So we'll crunch through all of these sooner or later. Some of these are just like a crazy overbound. So ammonia, right, is like almost double the lattice energy here, which is I think kind of interesting. Okay, for the sake of time, I might pause this before we run through the whole set so we can look at another one. Is that okay with you guys?
I have a question, sorry. Can you hear me?
I can't hear you, don't apologize.
Okay, so so we are dealing with gases, but we are having lattice constants, right? So how are those lattice constants determined? Obviously, if we decrease the lattice constants, the interactions will be higher. The energy will be increasing. If we increase the lattice constant, the interaction will be less, and the energy will be decreasing. So where is that number, that lattice constant is coming from?
Yeah, well, so it is. So yeah, part of the problem with running things through Colab is it's actually pretty hard to visualize the outputs. But if you look at what's happening here, we actually are like, we're doing an optimization on the cell parameters on the lattice constants, if I understand what you're saying properly. So we're not just optimizing the positions of the atoms, but we're also optimizing like A, B, and C, like the very like dimensions of the cell, based on the stress. And so this is like, things want to be together a little bit, but they don't want to be too much together. And so it is sort of like we update the Hessian and we try to find the right value for the size of the cell essentially. And so that is like, you know, things that overestimate or underestimate weak interactions, we'll see that show up in like what the predicted cell volume is. And so that is in some sense like a probe of like how accurate these things are. Does that answer your question?
Oh, yes. And so you have like for carbon dioxide, you have 4 molecules inside the box.
Yeah.
How those numbers were chosen?
Yeah, great question. Let me just show you the paper because I've talked about it a little bit. This is like, I think one of the best benchmarks. So these are like what the cells look like visualized. I can load them into Rowan later if we want. Like what the unit cells are. And this is just like people experimentally measured for these like structures, like what the measurements is. So this isn't a computational benchmark. This is like people did experimental data and like tried to actually measure the lattice energy for these crystal structures. So this is just what we have data for.
And the name of that paper, just to show it for the video recording?
Revised values for the X23 benchmark set of molecular crystals from physical chemistry, chemical physics. I'll send it in the chat.
Thank you.
Yeah, there's others. So you can do, I mean, you can do a lot of stuff. You can benchmark thermal conductivity. You can, I mean, pretty much anything you can think of and you can find data for, you can usually find a benchmark for. This is just one that fits nicely within a collab and doesn't involve like a ton of MD. So, you know, another thing you can do is liquid densities, right? So you can create a box of liquids. You can run an NPT simulation where you keep the pressure at 1 atmosphere and you keep the temperature at room temperature and you try to match, you know, like we know water has a density of 1.00. When we run with this model, a box of water, what density do we get out? Or, you know, what about 50-50 water ethanol? Or what about like an ionic liquid? Or what about uranium at 1000 Kelvin? You know, like, so you can do all this stuff to try to find where things break and don't break. Just the same way as you can with DFT. Like, what's the boiling point of this? What's the freezing point of this? The problem is just that, like, you know, some of these things are easier to like put in a little function and loop over than others. So trying to run like 300 picoseconds of like liquid MD simulations and converge that in like a live demo is just a little bit harder, if that makes sense. All right, let's see where we're at. And if it's not, we'll probably just cut it off around here. Oh, hey, look at that. Okay, so I'll copy those in a sec. So what I wanted to do is just show like, here's how easy it is to do a different calculator. Like we just now, so here we loaded in the MACE MP01 from that repo. Here now we've loaded in the orb calculator from the orbital materials repo. I'll just show the repo and I can send the link in the chat as well. This is like orbital materials. They put their model out there. It's free, it's open source, it's good for academic and commercial use. So you just swap calc equals orb calculator, and then you click run. And this one, orb, is actually notable because it's significantly faster. So orb is like a speed optimized model. So you can do things like MD for longer time periods. And so this should be a little faster to run. Yeah, so I mean, I think one of the themes that I want to get across here is like, if you're doing computational stuff, basically it's like a little bit too easy not to try this. Somehow we skipped some numbers in the middle there. I don't know what happened. We went from 12 to 17. That's okay. It's probably a bug in my code. I'm going to worry about it later. I think the point comes across pretty well. So like, yeah, if you do any sort of like computational stuff, you should definitely be looking at these, because when it works, it's like, it's just extremely good. And even if it doesn't work for the final answer, it can help you clean things up or get reasonable results much faster than like a conventional simulation, or scale to things that a conventional simulation could not. Okay, oh yeah, so here's some orb results. We're almost done here, so we'll just let it finish, and then we'll see sort of who does better and if either of them are any good at all in like an absolute sense. Yeah, and I promise the next demo I do will be much more visual, because this is really just staring at numbers on a screen. Yeah, it's kind of like the Matrix. It leaves something to be desired from the sort of intuition of chemistry perspective. All right. Come on. Gonna download this. I wonder if Google stopped maintaining Google Colab or something. Oh, there we go. I feel like I've had a not very pleasant time working with it over the past day. All right, so this is, do we skip one here? We skipped 18. All right, yeah, so I think when it can't converge, it's just skipping it. So we could add a smarter convergence check, but really this is gonna be fine for the sake of this. All right, so we'll say here, Mace MP0, this is orb D3 V2. Okay, and so what do we learn from this? Like what's our conclusion here? So if we go to the bottom, so these are our reference energies for the lattice energy, and this is a reference volume in cubic angstroms for the cell. Oh, sorry, this is the volume per atom. This is the volume per cell, just modulo the number, but it doesn't matter. And so here we can see that Mace, if we just ignore these rows that didn't run, I think these are even counted as zeros in this formula, but Mace overall, it has like a 13 mean error. So let's okay, next plan, let's delete all of the ones that didn't run because they're gonna mess up our comparison. Boom. That work? Yeah, okay, so yeah, we'll delete these. All right, debugging on the fly. Fantastic. So we have here, like for lattice energy, we have a mean error of 11 versus a mean error of like 24 for orb. So the energies seem pretty not amazing here. In particular, this one, it could not be worse. So cyanamide. So for those of you keeping track at home, that's this molecule. Yeah, cyanamide. Something about this molecule really orb does not like, and we're way overestimating the lattice energy. So this is sort of what I mean, where like you want to check that the system you're studying is normal, because you do sort of see these hallucinations with today's models sometimes. On the flip side, the volumes from orb are really good. So even though the energies are bad, the volumes are pretty solid. And so, you know, we'd want to obviously do much bigger tests than this, but depending on what you care about. So if you're trying to screen for like a specific like cell volume or like structure, this might be decent. I'd say neither of these are fantastic at this task because this really looks more like an organic task. This is less of a, you know, all these non-covalent interactions. But there is also a big speed difference here if you look. So the average time for Mace is, well, we can just put that formula in, is like 24 seconds, whereas here it's 4 seconds. So orb is like 5x faster, which about matches what they say in the literature. And that's kind of cool. Okay, so questions about this demo at all?
No, none here.
Yeah, I don't, so you know, yeah, these results are, they're like fine. They're not amazing. This is, I think, a task which I chose bad models for, but what it does show is, I think, like how easy it is to plug this in. And so how to like, especially using these like foundation models, stuff just works. Like it pretty much, you plug it in, you have to benchmark it carefully, but you don't have to be like a deep ML expert with access to like a battery of GPUs to deploy this stuff. So this was just running on CPU and it's still very fast. Obviously it'd be faster on GPU. What was I going to say next? Where am I at? Oh yeah, I wanted to show briefly, this is not an advertisement for my company. My point here is not to talk about Rowan, but I did want to show, we do have like a web interface for all this stuff, which makes it a little bit more visual. And so you guys can still see my screen, right?
Yep.
Okay, so one of the things that we make it easy to do is sort of like try to run and visualize all this stuff, like just like live, sort of in real time. So we can do like, this is for instance like a MOF optimization that we did to try to get the lattice constants for this MOF that I pulled from the materials bench. So you can see if we click play, like we load in the structure and it was pretty close. It's pretty good. So it goes down like 20 kcals in energy. And like the cell volume increases a little bit. You know, one of the nice things here is you can pretty much pull in like whatever you want because you have support for the whole periodic table. So this is like a nickel azide structure. And it, you know, you can run the optimizations in like, you know, a minute or so. This like took a minute and 21 seconds. And then you can also do some like significantly fancier stuff. So for instance, this is like a scan we ran for this like carbon monoxide binding to like a copper surface with various hydroxyls decorating it. I have no idea if that shows up well, but this is sort of the structure. So you have this like carbon monoxide here. You have all these sort of hydroxyls decorating the surface of this like copper slab. And then what you want to do is like study like, you know, this, how does this actually happen? Like if we want to form like sort of a formic acid looking thing here, how does this work? We want to oxidize this carbon monoxide. And we can actually run the scan with the neural network potential and sort of show it binding and then like hopping over. And we can try to estimate, you know, from this sort of CO bound minimum here, you know, up to here, we estimate like a 16 kcals per mole barrier for sort of the highest energy point here. You know, if you think that's like sort of a weird structure, like maybe this is a better transition state mimic, but this is, you know, like 10 or 12 kcals, so 11 above the minimum. And this is like, I'm not trying to say that this is like the world's most like elegantly done calculation. I was just doing random stuff the other day to to sort of try out our like copper slab handling. But this whole thing takes under 20 minutes and can be done like sort of, you know, just for free. It doesn't take massive compute or anything. And it lets you quickly, I think, evaluate sort of and look at geometries and structures in a very reasonable way. And so it's sort of just to show like how easy this is. And this is mainly enabled by the people who make the ML potentials. We just visualize it. We can like upload a file, so we can go to upload. I remember I had some CIF file lying around. Yeah, so this is like, it's like a random cadmium moth I pulled from the materials project. I think that's cadmium, right? Yeah, that's cadmium. And so we can go here. We like support a lot of different neural network potentials. So we can, you know, say, let's do this one with orb, I guess. Actually, let's do mace. I think it's more robust. And then we can say, let's optimize it. Let's optimize the cell constants here. We'll submit it to a job in the cloud, and then it like starts running. And so if we sort of refresh the view here, we'll start to see steps pile in as they finish running. I think just being able to view these things is pretty nice too, frankly. There we go. So you can see there's like little, you know, things are sort of flickering in and out on the sides of the cell. We see that the cell volume like increases a little bit, the energy goes a little bit down. And one of the other things we can do in these optimizations is like, if we want to track key bond distances, for instance, you know, like if we think this contact is important somehow, we can try to visualize this how this length is changing along the optimizations if we care about like these structural parameters. Yeah, so we've done 5 steps now, and this has taken like about 45 seconds. So you know, you can do the math. Like this is just, if you've done computations like this where you have to spend days, letting you do things like this that are like laser fast is pretty awesome. Yeah, so here we're started from an experimental crystal structure, so it's pretty close to convergence. So it only takes 6 steps. But I think this is just the real power of neural network potentials. Okay. Any questions on any of this shenanigans here?
Yeah, I'll ask. So, you know, let's say you've done this optimization step, neural network potential. I mean, what would you then suggest afterwards? Do you like then take on maybe a much more sophisticated functional and do you know, a single point calculation, or should there be maybe further optimization steps to see if there's any massive change, and if it all goes well?
So I mean, I think one of the difficulties and one of the things I think is underappreciated about like material science as a field, I don't know why I'm just looking at myself on the screen, is that like sort of the diversity and litany of like things that you care about doing is like so much larger. So like coming from drug design world, there people want to do like the same 4 things over and over and over again, and so you can get like hyper specific on what people actually want to do. In material science, like there's like, you know, what people want to do for polymers versus batteries versus like OLEDs versus catalysis is like all like very, very, very different. So it's tough to answer that in the abstract, I'd say. But in general, yeah, I think people use this 2 ways. One is like, if you're not sure if this is good, or you don't think that these results are going to be reliable or accurate enough for your application, then you can use this as like a pre-screening or pre-filtering step. So this is used a lot, for instance, in crystal structure prediction right now. This is starting to make it into the big companies, where if you're evaluating a ton of different structures or polymorphs, you do a pre-filtering step like this, and then you proceed to go on with the big guns. But you can essentially save the big DFT guns for like when you actually need it. The other way is like if you're confident in your area of simulation that like you have a model that works really, really well, let's say you fine-tuned it or you've just run a ton of really good benchmarks, then you can sort of use it as like a high throughput calculation thing where you don't need to go back and recheck the results. But I think either way, like it can still have the potential to be pretty useful. So if you like it either as like a pre-filtering step that saves you money but lets you get stuff at the same accuracy, or lets you get stuff much faster than you would otherwise. I think both can matter. And for instance, like, you know, just the ability to like just optimize stuff and like bind. So for instance, I just wanted to like generate like I just want to stick this CO to the surface of this copper here. And like I suck at drawing. Frankly, I'm not very good at drawing. So just the ability to like say I'll just run a scan and like watch what happens as it binds and watch the surface relax. I could then choose this for a DFT calculation, but I wouldn't have to do all of these essentially like trivial steps here on my like massive expensive computer where I'm like waiting in the queue to get time. You know, I can just do this on my laptop or wherever and essentially get these results for free. And then when I need the big results, I'll go get those. You know, so I think there's actually a lot of places where this can be useful in workflows. Does that answer your question?
Oh, yeah, for sure, for sure. I just, you know, I've heard about you wrote about composite functionals and things like that. And
yeah.
I've thought, you know, should I throw these composite functionals with the Gaussian basis sets at my periodic metal structures? I don't know if that's, you know, is that too different? Because normally it's just, you know, you do a periodic plane wave and you go with that. But there's not a nice pre-optimizer step. I mean, maybe I just make the energy cutoff lower and that goes a bit faster, or I use less K points for my periodicity. But I sometimes the gains in speed aren't actually that great.
Yeah.
So these are questions, and I don't know if there's an answer yet, because I think this field is still so developing that there's not a well-established, okay, this is how you want. If you want to go a little bit faster for high throughput, this is what you would do.
So I do think the future of high throughput, I think, is neural network potentials, right? So I think we'll always want these hyper accurate physics-based methods. I don't think the goal is to get rid of those, but we don't always need them. And for instance, like when you reduce the cutoff, you know, in molecular land, we just use smaller Gaussian basis sets. We make them as small as we can. Essentially, I don't have this data on this plot, but essentially what you do is you can't get it really that fast. You just start increasing the energy, like the slope of like speeding up DFT essentially curves like this on the plot. Whoa. So like you sort of hit some limit where like there's only so fast you can make it before the errors just get horrible. And so like if you do want like high throughput stuff that's still somewhat accurate for any simulation task, I think the ML surrogate function, like the NNP approach is significantly better. It seems, at least right now, it seems like that's the direction things are going.
Yeah.
So let me maybe just run through any other questions.
No, I think.
I have a question.
Okay.
I saw that you can do frequency calculations with Tron as well. How good they are, or you can't.
Yeah, so I mean, you get frequencies or like phonons, right, just from the second derivatives of the energy, so the Hessian. You know, an underrated thing about these is you can get that through backprop. So getting Hessians from like DFT is very, very difficult, but getting Hessians through backpropagation, you know, it's slower than just a single inference call, but it's not that slow in the grand scheme of things. So it works. We haven't done phonon benchmarks for like materials. Other people have done those. They're on MatBench Discovery. A link I probably should send in the chat, huh? What we have done is we've done like the vibrational, like IR frequency benchmarks, and those we find that like the good ones, again, the good neural network potentials are about as good as like DFT, or that like, you know, not maxing out DFT, like the best you can buy, but like average DFT, we're about as good as that for like vibrational frequencies. And so that does seem to work. I think this is, there's a paper on arXiv actually yesterday evening exploring training to Hessian. So using Hessian fitting in the loss function as like an interesting way to try to get robust neural network potentials from Justin Smith and coworkers at NVIDIA. So it's worth keeping an eye on this space, I think.
Thank you.
Yeah. So yeah, what I want to talk about now, just to close this out and then maybe do like a bigger Q&A thing, is like, so what now? Like, what are we missing? What's this going to look like? And what's practically useful for people in different walks of life? So we did like a little tiny demos just to sort of show where things were. A question that we've all been thinking about, like fine tuning, right? Like what does this look like? If the models don't work out of the box, like the stuff we looked at didn't work out of the box for lattice energies, what do we do? Amir did want me to do a fine-tuning demo during the presentation, and I said I thought that was too ambitious, but he was absolutely right that this is super, super important, and so it definitely deserves talking about. Yeah, and so basically fine-tuning, if you guys don't know, is just like you take a pre-trained model, like one of these big foundation models, and then you say, let's train it again on a specific subset of data. And the idea is you need much less data than if you just train something from scratch. So you're already, the model sort of already learns like chemistry, what bonds are, et cetera, et cetera. It just needs to like specifically study for this specific application. And what people have shown is like here, this is like a benchmark of one of the polymorphs of ICE IH. I forget which one that is. And essentially it shows that like if you're training a MACE model from scratch, you know, it takes to get like the correct density and energy, you know, it takes you hundreds of examples. That's not many for a foundation model, but you know, for a specific molecule, that's a decent number. You know, you have to be running hundreds of DFT calculations. Whereas if you're fine tuning from a pre-trained MACE, you actually only like a handful of examples already pretty much gets you to where you want to be. So with 50 examples, you get the density like exactly right, and you get the potential energy almost right. And then at 100, you're there, and you don't need any more data. So I think fine tuning is like a better solution than training your own bespoke models from scratch. There's code, so like this exists. It's pretty easy to do. So this is from the MACE docs, MACE-docs. You can get to it from the GitHub I linked. And there's like just an executable to fine tune on your data set. You do usually want to do like multi-head replay so that you like don't forget everything you learned previously. So they do recommend that. But yeah, so if you have a GPU and you have some data, you should definitely consider fine tuning a model. I think it's a really robust way to do it. And then you have more confidence that stuff works for your specific domain.
So when you feed it data, you know, do you just feed it that one best local optimized structure? You also give them like some of the steps leading up to it, like the trash file, and it also wants some of the not so good you know, stretches.
Yeah, so I think an important thing with neural network potentials is like they're much more robust when they see structures that are not just minima. So there's been a big move over the past like maybe 6 months to like try to do non-equilibrium fitting, where you show it structures where there's like some forces, you know, where the forces aren't all zero, because it's just much more information rich. So yeah, I think the trash file would be good. Another thing that you can do is you can sort of just like randomly shake things up. So you get to add Gaussian noise to every atom, compute all those calculations and get the forces and energies, charges if you want, and then like fit to those as well. You know, so that you learn like, oh, if these two get close together, they get really unhappy. And this leads to like much more stable simulations and sort of more robust, like more fault tolerant.
Yeah, okay. That's I think, yeah, some people for like absorption, they just literally bombarded randomly and they fed that to a neural net. And I know the third iteration of Facebook, Meta, and Carnegie's hackathon was specifically just global optimized structure. So I don't know how they ever did it, but yeah, there's been different discussions about that.
I mean, it's possible. I think if you're going to be doing optimizations or you're going to be doing like MD, like you're going to be dealing with structures that are not at minima. And like, I think it's important to try to consider all of this for the information theory lens. Like, am I asking my model to learn things that it just has no way of learning? You know, that's like, I think we understand, like, if you only show a molecule like certain elements, like if you don't show it any metals and then suddenly you start asking it to predict on like lead or iron complexes, right? Like it's not going to be able to succeed at that. Like that's just, you're asking too much. Like there's just no, even the best ML algorithm in the world with infinite parameters, I don't think can just like extrapolate to totally unseen elements where it's never seen anything like that before. I think there's a similar argument where if you've only seen like perfect bond geometries, perfect angles, everything like just as it should be, and then you start running MD, like it's not surprising that you see pretty poor performance in those cases, because there's just sort of like the information content of the training data doesn't prepare it for those tasks.
Okay, thank you.
That's a very qualitative explanation. Someone I'm sure could quantify that, but that's what makes sense to me, and I think is borne out by the data. Okay, so I think it's just worth like backing up and like trying to fit this into a conceptual model a little bit. So 2 slides on conceptual model and then 2 slides on future directions, and then I promise I'm done. One is just like, so for me, I said like, I was doing simulation for years before this was possible. And like, how does this work? Like we essentially are going from the ability where like you had to wait weeks to get an answer to now saying, oh, just put it on your laptop. Like you get an answer right away. And sure, in some cases it's not great, but like that's true for DFT as well. It seems like we're able to approach sort of the DFT limit. It seems at least like it should be possible with more data. And I think this is like sort of breaks people's brains a little bit, especially people who have been doing computation for a long time. And I think it's worth like trying to do a metaphor here. So this is like the Python logo. This is the C logo. And we know that Python, right, is an interpreted language. So you run a Python script. It's pretty slow, and then you get a result. With C, obviously, you have to first compile it, which is usually slower than just running the script once would be if it's a simple script. You generate some assembly code, right? But then once you've like done all the assembly code, it's like laser fast to get the right answer. So hundreds, thousands, etc., 10,000 times faster. I think we can think of this as going like neural network potential sort of in a similar way. So if we just have a single structure that we care about, we can solve the Schrodinger equation or an approximation thereof with DFT, right? And then we can get an answer. So, here's our whatever energy this is in EV. I don't know what this means, but like just an example of an answer you get from DFT. This is, this could take a few hours. When we do a neural network potential, we're actually doing something that's way, way slower. So we first have to run like, 100, 1,000, 10,000 calculations to generate training data. And then we have to train a model. And we get like this sort of like just a bunch of parameters, right? A GNN like you guys have been dealing with. But then what we've essentially done is we've taken all of the information that was in the DFT and we've like compiled it into this thing that then we can infer on really fast. And so I think that is like, for me, like a pretty useful mental model of thinking about how all this is done. I don't know that it's not magic. We just run a bunch of DFT calculations once, so we don't have to run them individually every single time. And then we essentially sort of like learn like some sort of representation of all of that knowledge in the parameters and then are able to infer over that. Another way to think about this is like, usually when we try to do approximate models, like semi-empirical theories or force fields, it's theory first. So we think of some like approximation, like, oh, what if we modeled torsions as a cosine? Or like, oh, what if we do a 12-6-4 non-covalent thing? And then you try it out, you run some simulations, and then you see if it works. So you might say, oh, well, this works fine for this, but we get the lattice constants wrong, blah, 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 blah. And then you sort of like, well, what if we tried a different theory? So then you think of the theory, you run simulations, and you see how it works. With NNPs, it's almost the exact opposite. So first we take the data that we want to model, and we don't come up with a theory at all. Instead, we just train an NNP to match that data. So instead of being like theory first, it's data first. And I think this lets us come up with like much, much more flexible and efficient, like domain-specific theories almost, that we would never have been able to come up with through manual parameterization. So if you want to train like an NNP that just handles like ionic liquids, you can do that. Whereas it's very difficult to think of like, what would a DFT functional that can only work on ionic liquids be? Like it's really not easy to think about what that looks like. But just by choosing the data we want to model, we can come up with these like hyper efficient, hyper specific models that have really, really good performance. And, it seems like there's limits to all of these models. Like we can't do like crazy massive metal clusters or electronic excited states. And I think that actually is sort of why we're able to get such good performance. So it's not like there's free lunch. It's not that like physics is just bad. It's that we're able to apply this sort of like really powerful inductive bias through selecting our training data. And that's what gives us such good efficiency. And I think this really does tie in with sort of this big idea for machine learning, which is maybe getting a little bit like too famous. But it's this idea of the bitter lesson, right? That like AI researchers always want to build knowledge into their methods. Whenever you encode some piece of your personal knowledge, it always helps on the short term and you feel smart. But then later on, you realize that scaling is always the better solution. So encoding expert knowledge doesn't scale as well as just adding more data. And so we can think of like conventional force fields as like we're adding our expert knowledge about like bonds and non-covalent interactions and charge terms and all this. And NNPs are sort of the contrasting solution where we just choose a flexible architecture, we dump in a bunch of data, and that actually lets us scale to things we could never do before. And so I think that's actually a pretty cool. So where are we at? Like, where are the big challenges to the field? So I think one is just like things aren't accurate enough, so they should be more accurate. I think we'll get there, but like solvent interactions aren't great. Like big bulk materials are like sort of still a challenge. They aren't like covalently connected. So like non-covalent interactions like these molecular crystals are sort of tough, and like everything could just be more accurate. Sort of a more philosophical question is like, how local is atomistic simulation able to be? So one of the things that we traditionally think of as like a long range effect is like electrostatics, so like charge-charge interactions in electrolytes, et cetera. This is something which some models handle explicitly and others don't. So some you actually learn like a charge function and others you do not. I think this is a big open question on whether that's necessary or whether like if you just scale learning, you can implicitly learn that as well. And this is like really, really hotly debated in the literature right now. NNPs are a lot faster than DFT 0.3, but they're still not as fast as conventional force fields. And so it's very, very difficult to scale to huge systems like proteins, polymers, like big boxes of liquid, et cetera. A ton of people are working on this. So like specialized GPU kernels, coarse graining, better architectures, quantization, distillation, et cetera, et cetera, et cetera. There's probably 4 papers published on this in the past week that I've seen. So this is like an open question. I think it'll be solved, but I don't know how. Point 4 is like very pragmatic, which is that in this case, we can actually generate simulated training data. So we can run DFT calculations. And the question is like, how do we do that most strategically? So we actually have the luxury that we can generate data in silico in this field. So how do we do that? Like, do we want to, like Amir was saying, do we want to do trajectories? Do we want to do random perturbations? Is it better to have more poses on fewer structures or like one pose for a lot of structures? Is it better to have a ton of like low quality data or like a tiny amount of very high quality data? Should we try to, how do we mix in experimental data? If we have like experimental densities or frequencies, how do we train to that? So this is, sort of fun. I think another question is like, how do we combine these? I think of NNPs as like physics-ish methods because they act a lot like physics and they reproduce a lot of the behavior of physics. Clearly, they're not like fully physical because it is an ML model, but it's different than like matter sim or like diffusion models, which are like much less physical, I think. And so the question is like, how do we, these two things are, I think, in many ways very complementary. So like, how do we combine those for various tasks? Can we generate trial structures with like a diffusion model and then score them with an NNP? I think this is like something that is going to like demand a lot of focus and attention. And then I think the biggest question for people like you guys is just creativity. Like, we're able to make a lot of simulation tasks now like 1 million plus times faster. Like, what do we do with that? This is something that people have been dreaming about literally for 100 years in like the quantum physics, quantum chemistry regime. Like, what do we do? Like, this is like such a fantastic time to be in this field. And I think one of the things, sort of our answer to that here at Rowan is like, we want to build like the Microsoft Word or like the SolidWorks for chemistry. So, back in the day, you needed like a big computer to do word processing or like these sort of computational tasks, and it was very clunky and like specialized. And now we have these sort of like user-centered applications where, everyone can have this on their laptop. It's just part of how you interface with the world. In our case, we want to take computational chemistry out from the supercomputer and make it something that like any scientist can do for their research. And so that's sort of like our vision of what we're trying to build with Rowan and why we're so excited about NNPs, because it actually makes it fast enough for us to do this. But I think there's many things to be excited about beyond this. And I'm curious to talk about that or hear what you guys think. Anyhow, blah, blah, like DFTs everywhere. More people should be able to do it and use it for their research. So yeah, we're a team of 5. This is more appropriate for an academic talk. I'm really curious, I think, just in the remainder of the time we have, just to like discuss this, hear what you guys think and sort of dialogue about like how this can be useful and where for you guys. So that's all I prepared.
Okay, I guess we're clapping, so first you'll leave it clapping for you. Okay, does anybody have a question? I'll let the audience if they have one. Okay, yeah, I guess I'll go. I've just, for me, it's always been the high throughput screening. I'm in lithium sulfur, so we have our adsorbate is what's called polysulfide. So the issue with that is it's exotic. It's not, if you look at Meta's big database that they made and they're with Carnegie, they did CO2, CO, oxygen, ammonia. So those people in those fields, they had a field day. They got it all done for them by a big company. But a lot of us, for the rest of us, for absorption, we're sitting here with these, maybe if you're in water treatment, you got some chemical runoff from agriculture. Like, we're kind of on our own here. And yeah, the models learn a lot, but you probably have to fine tune that because those are just, you're probably extrapolating or something. And it's just, you don't know how to navigate that field And like, I don't feel confident to be like, just publish this and be like, yeah, this is how I did it. And I think it's worth showing, but I don't know if it's like, they're like, well, this is not legitimate. This is not standard protocol. And it's just like, well, what is the protocol, right? When you're going into exotic, metal slab, periodic structures. So that's been one consideration.
Well, I mean, I think there's two ways that we think of interfacing with computation, right? And one is like much more difficult to think about from the publication perspective. One is like the computations come at the end of the project where you learn something from it that you want to publish as like figure 4 or whatever. That was always the joke in organic reactions, which is like you develop the reaction and then you send it to Ken Hauk and he makes you your figure 4 so it gets into JAX. Like you've already finished the project, you just need some computations to make it look good. And that, like, I think you actually can learn a lot that way. I make jokes, but like that, it can be useful. And then you need to be really, really careful about like how you run the calculations, how you benchmark it, all that stuff. And you want to adhere to best practices because that like the calculations are not easily testable. I think when you're doing calculations for high throughput screening, it's very different because like in some way you're the person who needs to care most about if they're correct. So like if you find a new hit from like a virtual screen, you almost don't even need to publish it, right? Like you can publish the method if you want to. It does make you look smart, but like fundamentally, you're the person who you need to not be tricking, not the reviewer. Because if you find a good result, then you know it works. It's already done what you wanted it to, right?
Mhm.
So yeah, I don't know. I mean, I think you can look at like various papers who have fine-tuned it. I think there is a consensus around this. Like you probably want to run good DFT calculations on the systems you care about. Probably like R2Scan is like what's emerging as the standard, or PBE, right? With like the appropriate cutoffs and everything. You make a set of those, you wiggle them around, you choose some candidate stuff, and then you compare the error against that, and then like you can fine-tune it, show that the error like approaches the reference, or like error relative to the reference approaches 0, and then I think like calculations are never 100%, right? Like the true proof is always in the experiment, but like I think at that point you've been responsible in my mind.
Yeah. The next thing too is the big tech players and stuff. Everybody's focus seems to be on just creating massive swaths of generating periodic crystal, all these sort of crystal structures or 2D crystal structures. It's just, sure, they make 1 million of them and then they'll say, okay, there's a good 40, 50 here that are a good candidate for some application. But I find like, are we moving towards models that are more applied, like more for adsorption, more for, I don't know, another application, but I find the focus is to make all these crystals, and I said, you're making too many crystals. We need to apply. We need a bit more application of it. I don't know if that's the next thing.
I'm inclined to agree with you, right? Like I think, frankly, most of the people wandering into this space from big tech don't really care about the applications that much. The reason why like Google or like Fairchem focuses on this, from what it seems to me, or the Microsoft AI, whatever their team is called, I don't think it's that Google plans to open up like a materials discovery business. Maybe that's what they're working on, but that seems unlikely to me. I think it's part of a way of like they see AI as a core competency for these big tech companies, which in many ways it is, and they want to make sure that they're on top of AI in every field and that they're like learning. It's like a gym for them, They're like going to work out at the AI gym to make sure that when they optimize the YouTube ads next, they get it like as good as possible. So I think they don't really. Yeah, maybe this is just wrong, but I do think a lot of it is like the reason this stuff gets funded at Google is just like it's sort of interesting and it seems hard, and like it's good to have smart AI people working at Google, and you have to keep them doing something when they're not doing the YouTube ads. So like, I might as well. I do think, right? So part of the question is like, what does the future of this look like? Do we look like a ton of different, is there going to be like a lithium sulfur model fine-tuned for that in the future that's super applications focused? That's one answer. Another answer is like maybe the models will just get big and really, really smart, and then they'll start to work for everything. Like we'll just be as good at DFT at like virtually everything with like once we hit the 1 billion or the 10 billion parameter mark, and then we won't need specialized models. I think we don't know, right? I think what we are seeing with like, I mean, it's very analogous what we're seeing in like LLM space. So I think if we watch the LLM space, we can imagine the dynamics playing out here as well. Like, small models are always better than like fine-tuned small models are always better than like the non-fine-tuned small models. But then while someone is fine-tuning a model, someone else is making a bigger model, and then the bigger model is like just as good as the fine-tuned small model, and you don't have to fine-tune it. So I think we don't really know how that's going to finish playing out. Like, big models are good. Google also dropped their like distilled small coding model Gemma 3 today, like a couple hours ago. That seems really, really good. So it's sort of tough to know. And I think the same thing will be true here. My guess is you'll see a spectrum. So there'll probably be like a protein specific model just for proteins that's like really small and really good at proteins. So you can run your like mega long protein structures. And then it'll have some sort of Swiss Army knife models that are good for everything. And maybe some, maybe some researchers will have like hyper specialized models just for their own like specific area of work.
Yeah, I think like Orb at least, I think they started an actual physical laboratory where they're doing stuff for CO2. So they have their own personal end application in mind, at least for one project. So that is interesting to see. Still, I don't think anybody else has any question. Yeah, I'll ask one more. So I don't know if you've seen it for your medicinal chemistry. We're kind of seeing here and there was this MRS AI event last week. Some people are doing these quantum variational and autoencoders to train some other, I think, a neural net potential. And that's, for me, I'm like, okay, that's at least 5+ years ahead. I'm not going to bother yet to learn quantum computation. I don't know if maybe it's closer than I think. What have you seen?
Yeah, I'm like, so me personally, I don't want this to be the opinion of Rowan. I don't want this to be the opinion of like anyone who matters. But like me personally, I put myself down as like pretty skeptical of the quantum computing applications I've seen. So I'll share. I put a blog post write up of this where I laid out all my thoughts with sources. But like, a lot of people like attribute like, oh, quantum computing is going to be great for drug discovery. Oh, it's going to be crazy. Oh, it's going to be so good for drug discovery. And then you sort of look at it, like the things they actually say, and you're like, well, this doesn't seem like it matters that much. I think fundamentally, like for a lot of the quantum computing applications, it like it like makes you much slower and like somewhat more accurate. But like for many cases, at least in drug discovery, like accuracy of DFT is not the issue. It's like the speed and the scale. Like, yeah, you can get 50 atoms right, but like what in drug discovery matters is 50 atoms, like nothing. Like it needs to be big. You want to model proteins, you want to model membranes, you don't want to model 50 atoms. And so like NNPs for me is like the direction of like maybe slightly less accurate, but like much faster. And that to me is like a much, much more interesting direction scientifically. I don't know the quantum ML stuff. I've like you were saying quantum variational autoencoder. I don't know. I've seen a couple presentations on this and I've never been like that impressed because like the regular ML is just pretty good. Like usually the speed of training is not usually the problem. It's like the data, and the better quantum training stuff doesn't get you more data. So at least for science, like I think we're so often data limited that I don't really see like throwing qubits at the variational autoencoder is giving you that much edge. But maybe people will think of some clever stuff and I'll look stupid. Yeah, I don't know. It's I try to keep an eye on the space, but I have yet to see anything that makes me think like, oh wow, that's awesome.
Yeah, okay. I'm sort of similar. I look at it and I look at their circuits look like spreadsheets of music or whatever, and I'm like, where are we going with this?
I mean, it's cool.
So,
Like, it's undeniably cool science. Like reading it all, it's like it's really impressive. I just don't really, at least for like chemistry, I don't really see the urgent point. Like I just don't really see the application. It doesn't seem to me like it's $1 billion opportunity. I do think on the variational autoencoder point, I think representation learning for like molecules and materials is like pretty under. This is not an NNP task, but like trying to figure out like better data rich representations of things, I think is like still underrated and like deserves more attention. It's something we've bounced around here at Rowan trying to figure out how to do that well. I don't think we don't have any like genius ideas yet. One of the things people have talked about is trying to take an intermediate layer of like an NNP and use that, as a representation, like as an embedding for a molecule. And I think sort of even like taking that step back, like sort of like interpretability, like what are these things doing? What can we learn? Like if an NNP is learning chemistry, can we like crack its head open and like figure that out at all? People have done that a bit for the protein language model space, but not yet in the NNP space. So I imagine people are working on that and I'm excited to see what they come up with because it might be cool.
yeah, okay. Okay, Eric. Yeah.
Thank you for presenting. Can you hear me?
I can.
You mind showing your website and kind of doing like a quick preview?
Yeah, for sure. Let me do that.
Is it free to use?
It is
Yes.
free to use.
No way. Nothing is paid.
Well, there is a premium, but you can also
Yeah.
get more credits as a student.
So what we do, yeah, so we try to give a lot of time to academics. We can't give away unlimited free compute because that's a great way to run out of money as a business. And letting people run unlimited DFT on your website it's an expensive proposition. But we have a ton of graduate student users, and most of them never hit their limits. So we're trying to give away as much as we can without running out of money, basically. So this is the labs.rowensci.com. You can go to, I'll put this link in here. You can just sign in with your Gmail. You don't have to like give us your password or anything if you don't want to. Not that we would steal it, but you know. And we have a lot of essentially different workflows here that you can pin or do things with. So we can predict redux potentials, bond strengths, like spin states, solubility. This is kind of a fun one actually.
This is new, by the way.
Oh yeah, this is pretty new. Oh no, hold on. I clicked the wrong button here. This is so new, I can't remember how to do it. So we can we have an ML model here for predicting solubility. That's kind of cool. And so the idea here is it's sort of supposed to be like a Google Drive for computational chemistry. So to make it like easy enough to use that like, you know, you don't have to be an expert in using the software. You just have to know what's going on with the chemistry. So we try to document everything we're doing here, like in various log files, and make it just like transparent and reproducible for the world. I'm trying to think what else. Oh yeah, so here like you can store everything in folders. So this is the calculations for the workshop here that I did just in preparation to try them. This is like what the transition state looks like for this. And it's supposed to just sort of the goal is that it all just sort of works. So like it's fast, it works out of the box, and you don't need to like waste time trying stuff out or like fighting your software. Yeah, I'm trying to think what other demos. There's like the visuals are like you can tune the visuals, you can do all sorts of stuff. You can load and edit like 2D and 3D structures. Oh yeah, so here's the predicted solubility for this molecule in like a variety of different solvents. So like it's supposed to be soluble in ethanol. It's not supposed to be very soluble in hexanes, which like makes sense. And this works on polymers too, for polymer lovers out there. Yeah, I'm trying to think. I think this is that's my ultra fast demo. You can go to our website. We have video walkthroughs for a lot more stuff. If you do want to like dig in, and we have like a documentation site where we like document how everything works for like SIs and stuff. So we are doing things in a way that we hope is like rigorous and reproducible.
Okay, thank you.
I appreciate it. Looks very cool. I have one other question. You mind going back to your slideshow to show off your team?
Oh yeah, for sure. Wow, so many questions that I was not expecting. You know, trying to make sure this is useful and not just talk about me and our company the whole time. But yeah, so our team is 5 people. So here we are, or here some of us are. This is my co-founder Ari, who handles the business in like front end and graphic design side. Jonathan, who's at Schrodinger Material Science, former like polymer chemist. Spencer, who's a software engineer from Meta, who keeps everything working, and then Eli, who is in charge of training our own models and like the whole ML side of things. And then this is me in my short shorts. I do mostly a lot of the chemistry and drug design facing stuff. Yeah, and we've had the privilege of working with a bunch of collaborators on various things. So Merck, MIT, Harvard, Michigan State, Colorado State. So we're working on a lot of like collaborative projects with like various academics trying to benchmark or develop new models. So yeah, just trying to build useful tools and stay on top of this space, and you know, hopefully one day make something that helps people do science better.
Thank you. Appreciate it.
For sure. We also work with classes. So we've been in a lot of like classes are using us now for like helping students run calculations. So if you're a TF and you want to do that for a PSET or something, happy to email and we can try to set that up. I don't know if that's relevant at all for what you guys do, but you know, it's kind of nice.
Yeah, we have a couple of courses or 1 or 2 graduate modeling courses we've had. Yeah.
Yeah, I know we partnered with the MIT like physical organic course. It's just kind of nice. I mean, I think computations, right, are now in like over 1/3 of like papers, at least in JACS, the American Chemical Society journal. And like, It's like, so I felt like when I was in school, we basically didn't cover computations at all. And then when you like start doing research, you're like, why does every paper have computations in it? And I was not taught anything about this virtually. So it's like, I think part of it is it's like tough to integrate, right? Because it's tough to teach someone to use VASP or Gaussian or whatever in the like in a week. And so, you know, Rowan at least solves the problem of being really, really hard to use. So you can like give an undergraduate who's never run computations before, like a link to one of our YouTube videos and they can figure out how to do it, which I think is cool. And ideally it works sort of as like a virtual lab a little bit. I think you do conceptually learn a lot about chemistry when you start having to run calculations, because you actually have to think about like where all the atoms are, which sounds stupid, but like you don't always have to think about that when you're just drawing things on paper. You can have a little bit of magical thinking, and like computations sort of hold a mirror up to that and like force you to think everything through in such detail. Yeah, that's I'm biased though.
Okay. I think that's it for questions. I don't see any questions from the virtual audience. Nobody's raised their hand. I know a lot of people don't talk. I think they're experimentalists, so they don't want to ask because they're scared of looking like they don't know.
I mean, that's the whole point of Rowan is like to make software that experimentalists can use. Because I did a PhD with all experimentalists. I was like 50-50 and like they couldn't do any calculations. So our hope is that we can fix that someday, right? That's the whole point, is like, you guys are very smart people. I can't see your smiling faces, but I'm sure they look very smart. You should be able to use tools for your research that like without someone like yelling at you or you having to learn how to program in like Fortran. So that's the goal.
Yeah.
Thanks, guys. Thanks so much for the time. And feel free, anyone, to reach out. I'll send my email in the chat, or Amir can give it to you. I would like, I'm happy to talk to anybody, answer questions offline, or just, you know, just bounce ideas around. So yeah, if I can be useful, please let me know.
Yeah, no, I've been to like 1 or 2, 3 of these, you know, AI for materials or chemistry workshops, but most of them are really just, this is the project we're doing, the professor talks, and I mean, they look like they're getting good results. Then I'm like, okay, but we're like on a different field here. Like, where do you even begin with this? What does the code even look like? And yeah, that's why we had, you know, we had to drag you in here too, to at least show what it's like to import a Mace model from the GitHub and stuff like that. And
Yeah, I will say, like, if you really know what you're doing, you shouldn't be doing it through Rowan, right? Like, if you want to do like massive MD simulations or big high throughput screenings, you should probably like do it through like just import the models yourself. We're gonna start publishing models soon, so that'll be possible. And like, it is worth, like, if you need to have tight control over the stack, that's great. I think for Rowan, like, it's very good for like the people who don't need to be experts in like the specific simulation part and who just want to be experts in the science without like needing to dig super, super deep into like learning the ins and outs of ASE, for instance. So.
okay.
Yeah.
I think that is it for questions. I will leave you then, I think. I think you've given your email, everything. So
Yeah.
thank you very much, Corin. Once again, if everybody can clap. We're clapping. If you can hear now, you can hear.
Thanks, guys.
Thanks so much, Corin. I'll write you back when afterwards and everything. Yeah, this will be uploaded on YouTube in case anybody missed the beginning or etc. So thank you very much, Corin. Thanks
Great.
for
Awesome.
sharing this with us.
Yeah,
Bye.
thanks, guys. Hope this helps. And yeah, hope to connect with you guys. Cheers.
Bye.